This session will be more about condensed matter. I think we will be very closely connected to what we already discussed previously. The first talk will be given by Professor Subir Sachdev. He will tell us an exciting story, kind of tell the story a little bit about the Paramagnon fractionalization theory or cuprate pseudogap.
Okay, thank you very much, and thank you also to the organizers, Eugene and Fabian and Annabelle and Marcus, for organizing a wonderful meeting. I'm really enjoying it. So we've seen yesterday, the cold atom view of things. Here's a famous phase diagram of Kopsel et al. Of the Hubbard model as a function of doping and temperature. At the time of this paper, this was at relatively high temperatures, and there was some crossover they call from polaronic, meaning there's a hole with magnetism around it, to a Fermi liquid behavior at high doping. And of course, we'd really like to understand this in some detail as a function of density, and then also understand what happens at lower temperatures. So on the condensed matter side, here's a sketch of a phase diagram of the same, well, presumably a closely related models, but not exactly the Hubbard model, of course, where you have, again, a crossover in the metallic states from a pseudogap metal here on the low doping side to a conventional Fermi liquid. So this is most clearly seen, for example, in photoemission. So if you look on the overdoped side, you see this large Fermi surface where the electron density, which is the electrons inside here, is exactly 1 minus p. And so this obeys a fundamental theorem called the Luttinger theorem, which says that in any metallic state, the volume enclosed by the Fermi surface should be the same as the free electron value. And that's accurately observed, in various observations here in the overdoped site. So that's certainly a big success of the theory. But on the other hand, if you look on the overdoped side, it's really still not a settled question of what's going on. You see these famous arcs, Fermi arc structures, which I will say more about, and I'll give you a possible theory for understanding these Fermi arcs. And clearly something, it can't be a Fermi liquid simply because you don't obey the Luttinger theorem if you think of it as a zero temperature state. So there's various views of this, that there's something fluctuating, some charge density wave or spin density wave is fluctuating, or pairing is fluctuating, and you're seeing some thermal fluctuating state, and that's all there is to it. And then when you go to lower temperatures, that's where you get the interesting quantum physics. So that's a valid point of view, mostly I think, but it's not a point of view I'm going to take. So my point of view is that really these temperatures, 200 Kelvin, is still a pretty low temperature. And it's reasonable to think of this as a quantum state. And so it should be a quantum state on its own right, with all the properties of a quantum state should have. And it's not fluctuation of something else. And so what that means more precisely is that at least in some universe, maybe not ours, or some other models that we can maybe make in cold atoms, this is a state that will survive down to zero temperature. It's a metallic state which could, in principle, survive down to zero temperature. And so that's the starting point of my presentation. That's the condition under which I'm going to understand the pseudogap metal. And if it survives down to zero temperature, then it's obviously a very exotic state, if for no other reason than that it violates the basic Luttinger theorem. So that tells us it cannot be smoothly connected to the free electron state, which is the basic property of any Fermi liquid. Okay. But starting from this point of view, then what we'd like to do is a simple mean field theory. The great successes in condensed matter, like BCS theory or Laughlin theory, have a simple mean field description and then a wave function even. And then from that, you can start and build the whole framework. So that's what I'm going to do. So I'm going to, this state that which violates the Luttinger theorem, we call FL star. FL means it's like a Fermi liquid. The star means not quite. It's got some fractionalization. And you can blame Senthil for that notation. Okay. Many other people have talked about similar state. They don't call it FL star, but okay, that's what I'm going to call it. Okay, so we start with this mean field theory, and then the point of view I'm going to argue for is that we should really think of this new mean field quantum state as like the parent of everything else that's going on at low temperatures. And in the real world, when you lower the temperature, this state, for various reasons, has to undergo phase transition, crossovers at finite temperature, but if it was really at zero temperature, there'd be sharp transitions to what's actually seen. Okay. All right, so the starting point really is to first describe this parent state, which is what most of my talk will be. And then I'll talk about more recent work and some speculations on what happens at lower temperatures. Okay, so this is, of course, there's been 30 years of work on this question, this point of view. Many other people have taken a similar point of view. Because of shortness of time, I'm not going to review all the approaches, including mine. I have had many different papers, which even I'm confused about. But I'll talk about what I think is the best approach. So this is the summary of my experience. This is the best way to do things, in my opinion. Okay, so this is work which started with a former postdoc, Yahui Zhang, who is now faculty at Johns Hopkins. Then Alex and Maria are current students. Eric is a student of Dirk Moore, who's at the University of Chicago. All right, so we start with our favorite Hubbard model that we've all been discussing in this conference. And we just use this very simple identity, which is exactly valid, that the Hubbard term can be written as the square of the spin plus some constant. Okay, and then you take the square of the spin operator and you do this Hubbard-Stronovich transformation. So you introduce this field phi, which will be the Paramagnon. It's some bosonic field representing magnetic excitations. This is phi here, and that phi is coupled to essentially free fermions. And now, of course, these fermions will form a Fermi surface and so that Fermi surface will damp out the phi, hence the word para. It's not quite a magnon, it's a paramagnon because there's some damping, which is quite intrinsic to the theory from the presence of the Fermi surface. Okay, so that's the theory, and now I'm just going to play a few tricks. The first thing I'm going to do is give it this phi some kinetic energy and some potential energy. And this is simply, you could imagine I'm integrating out some very high energy electrons and I'm doing some renormalization and that gives this phi some kinetic energy and V of phi. And even let's imagine V of phi is that phi only is a rotor, it only changes in orientation. So what I've done is I've mapped essentially exactly the Hubbard model in this square lattice here. This is a square lattice, looking at edge on, not one. It could work in any dimension. And I've coupled every site of the square lattice to a rotor, this blue particle which is moving on a sphere. So it's got some angular momentum, and that angular momentum has a coefficient J perp, so which means that the ground state is a singlet, and the first excited state is L equals 1, and the difference in energy is exactly J perp. So that's what I'm calling this. And it's got a whole number of higher angular momentum states too that I won't worry about. And there's some coupling lambda, which is this coupling here between the rotor and the electrons. All right, so now the next step is to forget about all the high angular momentum states and keep only the two lowest ones, L equals 0 and L equals 1. So I have a singlet and a triplet, and what better way to represent a singlet and a triplet but in two spins. So I'm going to take the rotor and split it into two spinor halves. And then now the coupling J perp is just an antiferromagnetic exchange coupling between these spins. So that's the ground state of these spins. The excited state would be a spin triplet, which can move around, and that is my paramagnon. So now I have a paramagnon, which is coupled to the physical electrons, which are free electrons initially, and then they're coupled to this spin 1 particle, which has been now represented by an auxiliary or ancilla bilayer antiferromagnet. Finally, the last step is I can relate phi, the field phi, to the spins S1. And that relationship is basically phi is S2 minus S1. Why is that? Because phi is the operator that takes you from a singlet to a triplet, and that is also the operator that takes you from singlet to triplet, S1 minus S2. Okay. So this is the model. And now you can forget the whole motivation and derivation. Let me give you a whole different way of thinking about it. So I have a Hubbard model here. And here I have a model of free electrons coupled to a bilayer antiferromagnet with a coupling JK, which is positive, and a coupling JK tilde, which is negative. So these are, you can think of as Kondo exchange because they are conduction electrons here. And now I claim is that if I do a 1 over J perp expansion, and I do a canonical transformation at large J perp, that's a very standard thing called the Schrieffer-Wolff transformation. You know, that's how you go from the Anderson model to the Kondo model, or from the Hubbard model to the Heisenberg model, do exactly the same thing, where now the large expansion parameter is J perp. Then to leading order in J perp, to order 1 over J perp, this model is just the Hubbard model. It's exactly what it is. At large J perp, you do a 1 over J perp expansion, you get rid of the excited states by a canonical transformation, and you will induce a Hubbard repulsion on these sites. So all I've done, at least to order 1 over J perp, is just rewrite the Hubbard model. I haven't introduced any, I mean, there are some new degrees of freedom, but they get decoupled in the large J perp limit, and when I decouple them completely, you know, this is like when you go from the Hubbard model to the spin model, there are doubly occupied sites that you decouple. So here also the triplet states have been decoupled, and you're back to the Hubbard model. All right. So everyone with me so far? This is just a rewriting of the Hubbard model. But of course, now I want to do more. I'm going to go to limits where J perp may not be so large, because this gives me a handle where I can now describe other phases, including a phase that actually looks very much like the pseudogap metal. And that can be done very easily. Yes?
So J-perp is large, I'm going to form singlets between its components.
Yes, correct.
So can you tell us again what's the value of U that you're inducing?
It's JK squared over J perp. So what happens is that if this is a doublet or an empty site, it doesn't couple at all to the triplet. If it's half-filled, it couples via J curve. So that lowers its energy, so that's basically how you get the U term. At higher order, you know, you'll get higher exchange couplings and all kinds of other things, but you can also put couplings here. And so there's a whole class of Hamiltonians, which is Hubbard plus various things. And all of that class of Hamiltonians can be rewritten this way. Okay, so now let's look at the effect of, so let me actually give you some argument as why we should even think about a regime where J perp is not so small, is not so large. Let's take this Kondo coupling. There's a Kondo coupling JK here and another Kondo coupling JK tilde. One is antiferromagnetic and the other is ferromagnetic. Now if you open your book on the Kondo problem, this is the famous Kondo RG. Right? If your Kondo coupling is initially positive, meaning antiferromagnetic, it grows to infinity, and you get the Kondo screen phase. So that is the physics of the Kondo model. On the other hand, if it's ferromagnetic, meaning it's negative, then it goes to 0. So basically, you can forget about the ferromagnetic coupling. It's going to 0. This is becoming larger. Oops. This JK is becoming larger. And so we could imagine that under RG, let me finish the sentence, JK has become bigger than J perp. And that will lead to the pseudogap. Yes?
This is true for one impurity, but
I know.
fork on the chain, that's...
Well, of course. So if you want to read the theory of the full model, there's an elaborate SU2 gauge theory I won't go into. But yes, I'm just motivating a rough argument that if if this Kondo coupling renormalizes to larger values, which is kind of reasonable, at least initially, then you should really think about a slightly different state that you're going to get when jk is bigger than jperp. Okay, so let's just now, with that motivation, let's just look at the phase diagram of this model as a function of the ratio of these two couplings. Where again, of course, the formal mapping, the Hubbard model, only works for jperp much bigger than jk, but after some RG, I can hope it works more generally. All right, so what happens now? So if I forget about the ferromagnetic coupling, and what do I have? Well, I have exactly what people call the Kondo lattice model, which is the heavy fermion compounds. There's hundreds of them, are all described by this model. And what happens in those models, essentially all of them, with a few exceptions, first either form a magnetic state, okay, we're not interested in those, but they form the heavy Fermi liquid state, where you get what's called the large Fermi surface, meaning you get a big Fermi surface that includes the electrons and the spins, and the mass of the electron is 1,000 times the mass of the bare electron, and that comes from having a Kondo coupling that's very large. But anyway, so what we know, and this both from experiment and theory, that this conduction electron coupled to a Kondo lattice just form a regular Fermi liquid, where you count the electron spins as electrons. Okay, so let's do that here. So how many? I'm thinking in terms of holes here, but this has holes of density 1 plus p. This is 1 hole per site. So the total volume of the Fermi surface should be 1 plus p from the conduction electrons and 1 from this. So that's 2 plus p. Now, but however, 2 is like a fill band. So 2 plus p in the Luttinger theorem is the same as p. So what you get then is a small Fermi surface of size p. But that small Fermi surface, I repeat, is a very, very natural thing. It's exact analog of what's seen all the time in the heavy fermion compounds. It's just a large Fermi surface, just the modulo 2 works out that it looks small. Yes?
There is one thing you don't quite want, which is a very large effective mass. Because in the pseudogap phase, or actually anywhere in the cuprate, the weighted or oscillator, the effective mass is limited by the super exchange.
Yeah, true. Fair enough.
So you need to get rid of that.
Yeah, so we have to do a mean field theory on its own right here, but you're right, yeah.
So this, sort of apparently violates Luttinger's theorem because it's a different state, but but are the particles still quasi-particles? Do they carry an electron spin and charge?
As far as the top 2 layers are concerned, this is exactly to answer your question. As far as the top 2 layers are concerned, it's a heavy Fermi liquid with electron-heavy particles. Just few of them, p, not 1 plus p. But it doesn't mean that this layer doesn't exist. So this is new. This is not present in the heavy fermion compounds. You still have this layer of spins. And these spins, they could break a symmetry. Well, then forget this whole song and dance. But they could form a spin liquid. So really, and this is the star, that is, because you're violating Luttinger's theorem by the top 2 layers of the original electrons, you have to have this fractionalized spin liquid here. Okay, so there are fractionalized neutral spin-a-half excitations around, and that's definitely a prediction of this. That if you get a quantum state which violates the Luttinger theorem, that's really a theorem actually, theoretical theorem. If you have a quantum state that violates the Luttinger volume, then you must have fractionalized excitations and emergent gauge fields. So if someday somebody measures at low temperatures a Fermi surface that violates the Luttinger theorem, that's effectively a measurement of a gauge theory or a fractionalized state. Yeah. Well, but there's broken charge order and so on, right? So it's not clear you're violating Luttinger's theorem yet. So by Luttinger's theorem, the best way to think about it is You take the actual lattice, whatever it is, it may have spin density, wave charge, take that lattice. In that lattice, you put in free electrons. You get a volume. Do you get that volume or not? Okay, so there is this other fractionalized objects that should be there. Okay, all right. So this is now my proposed phase diagram. So in the limit of large jk over j perp, you get this FL star, where these spins are forming a spin liquid, so some kind of resonating valence bond state here. And these two are forming a heavy Fermi liquid, which happens to have a small volume. And here's my wave function, the advertised wave function. The simplest wave function for these top two layers is just a Slater determinant. Just take free electrons in the top two layers. And this kind of wave function works quite well for the heavy fermion compounds after a projection that I'll come to in a minute. And then you take a favorite spin liquid for S2. So this is a problem, at least from the theory side. There's been an enormous amount of progress. People have classified and understood all kinds of candidate spin liquid compounds. The nice thing about this approach is all that work on the insulator, you can just take over with no change. This is also an insulator that's sitting there. You don't have to reclassify spin liquids in the metallic state. It's the same states. So that's really a big advantage of this approach when you go to the next step. And then you put a projection. You project, and this is numerically the hard part, which people have been trying but not much success so far. You project these two layers onto spin singlets, rung singlets. And then, so this is a wave function whose only coordinates are the C electrons. So this is really a wave function on the C sites. Everything else has been projected out, sort of like a good solar projection. You're back to the physical Hilbert space, and that's your wave function. So I would love to see, numerical progress in analyzing this wave function, and maybe computing, 3-4 point correlations that cold atoms see in the undoped side and see if there's any correspondence. And of course, then on the usual side, these form rung singlets, so there's really nothing much to do, just have free electrons, and these singlets disappear. So that's the Fermi liquid state. So to recap, here's kind of the canonical picture from day one of the high TC, starting with, I would say, I guess, Bhaskaran and Anderson and Kivelson et al., although Kivelson has since abandoned that point of view, that there's spin charge separation in the cuprates, where the electron with charge 1 and spin a half splits into a spin-on, which carries only the spin, and a holon, which carries only the charge. So this is the electron fractionalization approach, and I've written countless papers on this approach, but you run into trouble with this approach eventually when you try to relate to experiments, because you have to do something highly non-perturbative, which no one knows how to do. And the reason is that there's never been any sign of this particle. There's some sign of fractionalized spins, you can maybe see them, but nobody's ever seen a charge that has no spin. That's simply not ever been seen anywhere. And the reason is simple. If you think in the TJ model, it has two terms, T and J. The J terms like fractionalization. Yeah, you could imagine it wants to form a spin liquid. So maybe you can imagine the electron will fractionalize. But then the T term is a highly attractive interaction between the holon and the spin-on. So you may form holon and spin-ons, but as also in Eugene's work, they will just rebind. You're not going to be free. So because J is much smaller than T, this never works. If you had a model where J was larger than T, then this might work. But nobody studied those. I mean, theoretically you could study those, but those don't occur in the real world. So what we're really doing is we're taking of the original electrons, and they form a electron-hole bound state, an exciton with spin 1, which we call the Paramagnon. And what we're doing now is splitting the Paramagnon. So charge is gone. We're just splitting the Paramagnon into two spin-and-a-half particles. The first layer will combine with the electron to form the small Fermi surface, and then this will give you the spin liquid. That's the picture. Yeah. 5 minutes. Okay, I haven't even started my talk. Okay, no. All right. So here we have a theory. So now we can we do something with it? So yes, we take our mean field theory. So in the mean field theory, we just completely, to begin with, we ignore the bottom layer. So you just have the top layer and the first ancilla layer. And you just take some free fermion Hamiltonian for the ancilla layer. It must be adjusted so the density is exactly 1. And then in the slave boson theory, as you may know, what you do is you condense a Higgs field, which is the hybridization between the first layer and the second layer. And this kind of theory works surprisingly well quantitatively in the heavy fermion. So we just take the same theory. So now this has some free parameters. One is the value of B, and that will determine the size of the pseudogap, as you'll see. And the other are these hopping matrix elements. So there's 3 of them. We take T1, T2, T3. And these T's we know from the overdope side. All right, so what happens? I think the red line here is the dispersion of the C. The dashed line is the dispersion of the F1. So that's been fit to get the right Fermi surface. And then when you turn on B, you get the blue pockets. But if you now weight this by the electron spectral density in photoemission, this is what you'll get. So these are the arc structures, but however, there definitely is something very faint at the back. And so our proposal is this is what this experimental data is really measuring, although, in this data, certainly there's no sign of this thing at the back. There is this other paper by Peter Johnson's group where they claim to see something turning around, but ZX is skeptical of this. But anyway, it's published. Yes?
And the quantum Paramagnon rotor theory, are they capturing the same physics, or are they?
No. Yes. I mean, it's the same theory.
It is the same thing.
Yeah. So if I go here, so I said that this forms a. I take the Paramagnon and I split it into 2 spin halves. Then I say that these two form a large Fermi surface, like I said here. So the theory for that is the theory I'm presenting. That's all.
I see.
So there's a hybridization, which is the slave boson. Okay. The gauge structure here is quite a bit more complicated. I'm not going to go into that, but there's many lengthy papers on that. But the beam field theory is really the same. Okay, so continuing. So, then you can look at the antinodal spectrum. This is Z-axis data again. So that's data taken over here. So you look at the antinodal regime, you go scan momentum this way, and you look at a function of frequency, energy in the vertical axis. So if you're on the overdoped side or at very high temperatures above the pseudogap, you see the red line. So that's the large Fermi surface. Here's the Fermi points. And these 2 points here correspond to, they correspond to the 2 red points here, and the overdoped side. You have the big Fermi surface. But then when you look on the low temperature on the pseudogap, then you get the blue line, and so this has a gap. It doesn't cross the Fermi surface. And also the maximum of the dispersion, or the minimum gap, is at a different point than the Fermi point. And this led many people to suggest that maybe there's a pair density wave and not just superconductivity. We disagree with that. So if you take our theory, you can get all of these features and also get the same, essentially unchanged spectrum in the nodal region, which the pair density wave theory does not get. I'm sorry, I'm rushing. So this is in the antinode, this is the final Fermi dispersion, which is a hybridization of the red line and the black line. And this is in the nodal region, where you can see that the red line and the blue line are almost the same, meaning there's no change in nodal spectrum between the overdoped and underdoped. The blue line does have this turning around, and this is the back side of the pocket there. We'd love to see that turning around, but it's not been seen. But that's above the Fermi energy, so not so easy to see. So we've also done some work where we include the coupling to the spin liquid. So you just do an expansion in J-perp, and then there's some spin liquid susceptibility that's going to damp out this spectrum. So this is just free electrons. Now we're going beyond free electrons and including this second layer, which would not be present in a heavy Fermi liquid. So there's some momentum distribution function and energy distribution function. There's, of course, some free parameters. But let me just say, for shortness of time, we can fit, essentially all of the trends quite well. And many others have done these fitting routines with different models. And let me just say that we think we do better than any previous attempts. There are problems with all the previous attempts which we don't have. For example, the pair density wave has problems with the what happens on the nodal side. The spin density wave approach also has dispersions that don't quite work, and so on. Okay. All right. So to conclude, then, so that's it's a mean field theory with fluctuation, and there are fitting parameters, but we are very encouraged by how easily it just fits the data. It's not a proof by any means, but it seems like at least it's a reasonable starting point for understanding the data. Okay, so now this is ongoing work with various students and postdocs here at Harvard. Jonas was a visitor from Max Planck, from Munich. So this is my view of the world now. So I've just described this region. And I've also said a little bit about how when you have this transition as a function of J-perp over J-condo, that you have this, you go through to Fermi liquid, and in between we think there's a strange metal, and there's a complicated gauge theory here if you want to read about it. And we also believe that if you put in some random couplings in this gauge theory, you will get the strange metal linear resistivity. So that's another thing for cold atoms. The prediction is here, if you had a perfect crystal with no impurities, then the low temperature linear resistivity regime will not appear. It really requires spatial randomness. Okay. I'm done? Okay. Let me just, okay, so now, if you don't mind, one more slide. One. Yeah. Okay, let me just end with this slide. So what we are thinking about now are the low temperature transitions. And so here we really have to take the spin liquid into account in the third layer. And if you write the spin liquid in terms of bosons, you can get Néel order. And yeah, let me just show this beautiful data by Takeshi Kondo's group, who's seen whole pockets with Néel order with the backside at very low doping. And we think that can be described by theory here. And we are currently working on theories of spin-ons, fermionic spin-ons here, which are dual to this bosonic theory, which are actually now known to be pretty much unstable. So we have good reason for expecting this spin liquid not to survive down to 0 temperature. And we think it can lead to all of these things as possibilities. And okay, but that's not fully worked out yet. Thank you.
Great talk, Subir. Perhaps one remark and one question. So if I take a very, very practical point of view, right, the description with C and F and the hybridization,
right,
I can just see that as a way to deconstruct or reconstruct rather the pore of the self-energy that we need, we know from, if anything, from cluster DMFT and
right,
joint paper on that.
Yes.
That's at the one particle level what creates the pseudogap. So I can see this as a parametrization of this pore.
Right.
This actually just incidentally resembles also thinks that Imada and Sakai, I mean, maybe that's one additional reference.
Imada and Sakai, okay, well, I did mention YRZ, it also resembles YRZ.
Yeah, it resembles YRZ, but there is a whole, I mean, the Sakai Imada thing was introducing some ghost fermion, which is suspiciously similar to your F, to sort of mimic that. Okay.
Right.
But actually, my real question is about the
But
S2.
my comment is that all of those approaches don't have the S2, and we insist they have to
No,
be
they don't have the S2. That's absolutely
and
correct.
that's we claim that consistency requires
So
S2.
actually, my question was about S2.
Yes.
So what are the effective interactions in the S2 layer? Because at the very zeroth order level, I could just say, once I found the condo singlets, the C and the S1, I don't care about the S2, they could be free moments, right?
Well,
I want them to be free moments.
Of course not.
So tell me what are the...
Well, we don't know, so we just postulate some spin liquid, and you can try to figure out the interaction of the S2 layer. You'll get antiferromagnetic coupling. So you have an antiferromagnet in the square lattice with some sort of couplings. So, and we want it to be not ordered. We don't want a large spin correlation length for the reasons you described yesterday. And so it's some spin liquid. So the first thing, the simplest thing you can do is just in the pseudogap is just to perturbations in J-per. So then you'll get some damping of the excitations. Of course, right at the Fermi level, at the hole pockets, it won't make any difference because the hole pockets don't have enough energy to create these spin excitations. But at the antinodes, where you're talking about gapped excitations, then they will damp out. So these excitations really do play a role in getting these EDC curves proper, and even those they do a pretty good job. So this broadening that you get above the pseudogap comes from the S2 layer. That's what we claim.
So I'm confused about that. I thought that most of your fits to the photoemission was just from the C and F1 and
So that was the dispersion. So this is all dispersion where, of course, this dispersion is coming from a very complicated plot where you're just plotting the peaks. So the red lines are peaks of some curves. So if you just look at the peaks, yes, then that's a simple theory. Now we want to look at the whole line shape, not just the peaks. And I just have no time to go into that.
So you that with the S2 layer?
Yes. So if you want to get the full line shape rather than just the position of the peak, this peak here gave you those pictures I showed. Now you want to get the full line shape, both as a function of momentum and as a function of frequency. And that also works quite well.
So to do that, what did you assume for the correlation function?
Yeah, so the simplest model would be to take a SYK model. Then it's momentum independent and easy to work out.
Okay.
But we also took a spin liquid with a Dirac fermions and coupled it. Yeah.
Okay, thanks.
So that's harder computationally, but it's in the paper.
Sorry, let's take one action.
So going to your sort of big picture overview of all the different phases, do I understand right that at finite temperature those are all crossovers? Can you tell us what happens at zero temperature? Are those transitions?
Well, yeah. So like I said, me being a quantum phase transition person, I take all these phases and put them at zero temperature to begin with. So at zero temperature, everything here is a phase transition.
All 5 of those are different phases?
Yes. And so we try to understand that, and then we try to make some reasonable, something intelligent to say what would happen at the finite temperature crossovers. I mean, some things are of course phase transitions, like the onset of, if you have a broken symmetry like charge density wave. Also, let me add to my response to Antoine, this S2 layer is absolutely the crucial thing to give us all this stuff here.
Yeah.
Maybe the most provocative is the strange metal you're claiming is a separate phase, that's really a zero temperature, different phase.
Or it could be a critical point or a phase, depends on, In fact, in this theory, you get a phase or something. But like I said, what takes over in the real world at low temperature are these, what's really at low temperature here. These are like parents that are very useful starting points for thinking about things, I claim. Yeah.
Quick question. So, in the past, there have been theoretical predictions based on the YRC model beyond ours, for example, resonant X-ray. So, can they now be sort of basically predictions for your theory, or is there a substantial difference?
To the leading order, there will not be. I'm not aware of the resonant X-ray. So there are some differences between us and YRZ. In particular, YRZ, this dashed black line is somehow straight and has to go to pi over 2 pi. They have a very strange constraint that we don't understand. In our case, the black line, the only thing constraint on the black line is it has to be exactly half filled. That's all.
But the structure is the same, just quadratic in fermions with extra species. And
yes, so that's the mean field. The mean field theory is the same, but everything else is different after that. And we believe we have a completely consistent starting point. It's not an ansatz pulled out of a hat, which is, well, that was brilliant. They did it, and we'll give them full credit, but we have a real theory here.